Good morning. My name is Bannatyne. I am representing VORAGO Technologies. For those of you who are not familiar with our company, VORAGO are a fabulous semiconductor company based out of Austin, Texas. We've been going since 2004, changed our name at the end of 2015 from Silicon Space Technologies to VORAGO Technologies. And around the same time, we created a great focus on commercializing our technology that we had created over the previous 10 years. And our technology was mainly funded by a Department of Defense type research grants to come up with a way to harden standard CMOS process against radiation effects. And we do that by putting implants into the device to prevent latch-up. So our core technology is really the ability to harden CMOS by means of modifying the process. We've licensed that technology to other semiconductor suppliers, such as LSI and Texas Instruments, to create space-grade products based on this technology. And also we have been creating our own, I'd say, modest portfolio of memory chips and microcontrollers branded under the VORAGO. The nice thing about using CMOS is that we can access a whole bunch of foundries around the world. And really, that's what we're trying to do in this industry, is to leverage as much commercial technology as possible in order to make things more efficient and reduce costs. So we believe in leveraging commercial fabs like CMOS and also IP, such as the ARM core, because it's easy to develop with and there's a lot of software ecosystem out there. So that's really what our core technology is and what we do. The nice thing again about CMOS is that by making these implants, it doesn't affect the performance of the device or the yield or the power consumption. So it's an efficient way of hardening products against radiation effects. A bit more about our technology. We call it hard cell. And this chart shows a cross-section of a standard CMOS device. So it has an NMOS transistor on the left and a PMOS transistor on the right. And superimposed on top of that in red is a structure of parasitic transistors, bipolar transistors that exist on all CMOS devices. So as a byproduct of the CMOS architecture and manufacturing flow, all CMOS wafers come embedded with these millions of parasitic devices that typically, when they are not activated, will not be a problem, but in conditions of either extreme heat or electrical stress or radiation particle strikes, there's a danger that these parasitics become forward biased and switch on. And when that occurs, the condition is known as latch-up. And what happens is it creates a short circuit between VDD and VSS, and it can have serious consequences for the device. It can destroy the device, or best case, you would need to reset the device in order to get out of the latch-up condition. So this is really the most serious space radiation effect, is radiation-induced latch-up. The green area that I've shown is the hard cell implant, which is a horizontal and vertical component, and the purpose of the implant is to reduce the RP-well resistance and reduce the gain of the parasitic NPN. So it effectively stops the parasitic structure that looks and acts like a thymistor from switching on, and that's how you prevent latch-up with this implant. We complement the hardening by process by some more conventional means. So we add structures such as error detection and correction onto the memories to mitigate against bit flips that are radiation induced. So the way that that works is, as the CPU fetches a 32-bit word that looks at that word at a byte level, we can detect 2 errors and detect 1 per byte. And we further add a scrub engine, which is another circuit that operates independently of the CPU and the EDAC. And in the background, it sequentially steps through memory continually, looking for bit flips and correcting them before the EDAC sees them. And what that does is reduces the possibility of having a multi-bit error. I mentioned that we can detect 2 and correct 1, so we don't want to have 2 bit errors within the same byte, and the scrub engine helps us prevent doing that. In addition, there are certain layout techniques that we follow, so we separate logical bits by an entire byte. And what that means is that if a particle strike comes in from an angle, it reduces the possibility of taking out multiple bits within a single byte. We'll see that occurring. So that's how we protect against bit errors in memory. There is also some logic that we add to prevent or to mitigate against single event upsets in logic. And the chances are that particle strike would hit memory array before logic, just because typically these chips, the majority of them is taken up by memory arrays and logic smaller. But still a possibility. We replace all of the latches on the device with a structure known as a dual interlock cell dice latch, which has 3 floating elements within the latch. We add triple modular redundancy to the internal registers, and we add clock glitch filters to prevent a transient signal, a single event transient, from propagating through the structure. So there are various techniques that we deploy in order to protect against different types of radiation effects. So there's several ways that radiation can affect the operation of the component. The microcontroller that we created and are currently flying is shown here. It's an ARM Cortex M0, runs at 50 megahertz, and has a basic set of digital microcontroller peripherals. The radiation specifications are shown 300K TID, which is pretty high. The soft error rate is in the order of e to the -15. And the LET, linear energy transfer, is 110 MeV. We tested up to 160 when we were doing radiation testing recently at Berkeley. So the radiation tests are confirmed the specification that we created. We're currently working on a next generation part based on an ARM Cortex M4. Runs faster, it has more peripherals on board and more peripherals and floating point such like. So we expect the capability of that device to open up some more applications that it can be used. Another project that we recently undertook was to create a system in package where we took the microcontroller die and a radiation-hardened A to D converter, an FRAM die, and put them in a small package. And really, what's driving this is miniaturization. We've embarked on a couple of CubeSat board projects, and one of the things that we ran into was just the amount of space that you have to work with. To get all the components on is becoming more challenging as we try to add more functionality to the system. In one case, we found we were using a large FPGA and it took up almost the whole side of a 10 by 10 centimeter board. And we stuck 3 big memory chips, SRAM chips on the back, and it didn't leave us a whole lot of room to lay out the rest of the board and the other functions that we wanted to put in there. So the idea here is that we're trying to squeeze as much typical type of CubeSat functionality into a small package as possible. And our intention is to qualify that for flight. As packaging technology goes, people have been doing system in packages like this for a long time. Less so qualifying them for flight, and that's where we see the challenge of this project. This project is being funded by NASA. Also, we found that it's easier to get folks started on using our chips if we provide a larger part of the system. So we have spent a significant amount of time creating software in the ecosystem around the microcontroller to make it easy to use. And also we created a reference design for a CubeSat, OBC. The background behind this is a company called Pumpkin who provide CubeSat board-level components. Approached us and they said that they were increasingly getting more requests for a radiation-hardened controller, and they asked if we would be interested in putting together a reference design for a rad-hard board. So we took a micro, which is shown in the center of the diagram there, with some common components that are typically used around the micro. Everything that we tried to use was radiation hardened, with the exception of a couple of chips. The UART to USB, which is not intended to be used in flight, we disconnect the power supplies, and the CAN controller and physical layer chip. We couldn't find a rad-hard equivalent of this particular chip. So we've added some protection around the chip where we monitor the voltage and currents, and also with the spy port we look inside the registers, and if it appears that there's a radiation-induced problem with the CAN chip, we disconnect the power to that chip also and reset it. This board is available from Pumpkin. However, also we make all the reference design files, the schematic and the bill of materials and Gerber files available to anyone who would like to use it as a starting point and modify it as they see fit. Our design is based on the Pumpkin CubeSat kit bus, which is very many, so some folks have been interested in modifying it to use with a different bus or use different memories or other types of interfaces with this board, but it's available to download. I typically see the microcontroller being used in a couple of different configurations. The first one is, as I showed it on the reference design, where it's being used as a main system controller. Now obviously you're limited by the ARM Cortex M0 running at 50 megahertz. There are plenty of applications that require a higher amount of bandwidth for processing the control algorithm. The other configuration that I often see this device being used, which I think is pretty interesting, is as a watchdog or system monitor in a higher performance system. So on the right hand side, shows a system which was an X-ray event detector prototype system. The big chip, the heatsink, on the left-hand side of that board is a Vertex 5 FPGA, and those FPGAs can get expensive for the radiation-hardened version. So what I often see is designs where certain mission-critical components have been judiciously selected for hardening. So in this case, it's a commercial version of the FPGA, and it's being backed up or watchdogged by radiation-hardened micro. And that's a way of being able to reduce the system cost. If you have a mission-critical rad-hard component in there that you know will withstand radiation and latch up immune, and you can use that component to monitor the other commercial chips that are in the system and reset them if necessary, then that seems to be a popular approach in order to trade off cost with mission assurance. So that's quite a popular approach I see. It's a development kit for the chip. It's intended to create software. It's about $550. As I say, the nice thing about the ARM architecture is there's lots of tools and things like operating systems and such available for it. And I've left 29 seconds for questions.
I have three questions. Yesterday we saw a presentation to Europe, the Moon and Jupiter. The requirement was 900 or 1,000 kilowatt. Could you give me an estimation how much aluminum I would need for something, the technology you develop, if I want to protect something against such huge amount of radiation? Second, this is a CubeSat conference. Do you offer stuff for CubeSat prices, so to speak? And is there any ITAR related issues?
Okay, thank you. Those are all good questions. Let me answer them from the back forward.
Could I ask you to use a microphone, please?
Sure. Sorry. Let me answer those from the back. So the first question about the export control. These parts are not ITAR restricted. So they're controlled under export administration regulations. The export code is 3A001. It means that we can ship them to anywhere except a small number of countries with the appropriate documentation. So a distributor here in Europe, ABB, takes care of that documentation, so shipping them should not be an issue. The second one was the cost. They're more expensive than if you go to DigiKey and buy a commercial ARM Cortex M0, they're more expensive. But compared to conventional radiation-hardened methods of rad-hard by design or using boutique fabs and processes like SOI, then they're very inexpensive. So the plastic package version is $700 for the chip. There's a ceramic part that's slightly more expensive, I think $850. So relatively speaking, they're pretty inexpensive, and I think for a CubeSat budget, in order to reduce risk of radiation-induced problems, I personally think it's quite a competitive price to do that with. The third question about the TID. Okay, so we have dialed in the TID 300 kilowads. And actually, the earlier chips that we created, the TID level was much higher. Those were created for Department of Defense type applications. So we consciously dialed back the TID performance so that it would not be ITAR restricted and we could sell them commercially. The best way that I know of, and maybe there'll be some folks out there that have other ideas that chip in, of estimating how much additional aluminum shielding would be required in order to operate where you expect 900 or megarad or PID. The way that we do that is when we do our radiation testing, we create the data which is in the form of a Weibull curve. And with the Weibull curve, we go to a simulator called 2018.B.1.1, which is maintained by Vanderbilt University. It's online, anybody can go and use that. And by putting the data of the Weibull curve into the simulator, you can simulate different radiation environments, different types of solar activity, and also the thickness of the shielding. So I think you'll be able to figure out how thick the shielding would have to be using the 1996 probe. Do some trial and error. Off the top of my head, thank you. Yes, ma'am.
So you mentioned that the silicon used is hardened against electrical stress. I'm not an expert on hardware, but I'm curious to know how that hardening works or how has that been done.
Okay, so the core technology that we call hard cell is the implants that we put into the device early during the manufacturing stage, just below the transistor active areas, with the intention of not allowing the parasitic transistors to be switched on. And latch-up can be induced by different types of stress on the die, one of which is a particle strike where an ion throws itself into the die and creates these electron hole pairs that should recombine. But if they forward bias the parasitics, then that would induce latch-up. It would switch on the parasitic network. It's the same structure, it's the same parasitic network that would also be forward biased in the event of an electrical transient that causes a disruption of charge, disruption on the die, or also high temperature carrier creation can also forward bias those transistors. So it's the same mechanism that's used to immunize against latch-up and prevents the parasitic structure from switching on in the three cases of temperature, stress, or radiation. So it's really the same protection against that thyristor mechanism.
Final questions?
Thank you very much.